Hello students, today we'll be starting off with the first chapter of class 12, that is electrostatics. So, electrostatics, as the name itself suggests, that we'll be discussing about the properties which are related to electrons. How do I know that? Let me just break this word into two parts. These are the two parts, let's say, yeah. So electro, this comes from the word of electrons, and statics means at rest. Okay. So we have electro standing for electrons, statics standing for at rest. So all the properties that we'll be discussing in this particular chapter are going to be based on this concept, yeah. But before we come to this, let me just give you a very brief intro about what exactly is the thing that we will be discussing about. So that comes from the notion of what is known as an electric charge. So what do we understand by an electric charge? Right? Now let me give you an example. Let's say you have an atom. So when you have an atom, what is the basic structure of an atom? I'm very bad at drawing. So what we have is this. So let's say if you take a hydrogen atom, let's say, so we have an electron that is moving about the nucleus, right? So when we say I have an electron that is moving about the nucleus, so the nucleus should be having some amount of positive charge. It does have, because it is composed of protons and neutrons. Okay? So the protons take care of the positive charge and the neutrons are neutral. Therefore, the whole atom on the whole is neutral, right? So what we get as a result, we have understood that these are the two types of particles, subatomic particles that exist within an atom. Three subatomic particles that exist, but two are the ones that are most important for us. So what we see, we have an electron, we have a proton. Let's now try to understand about their physical properties. If we talk about the mass of an electron, the mass of an electron is given by 9.1 into 10 raised to the power minus 31 kilograms, whereas the charge, if I say, the charge, so this charge is like mass, a physical entity. It is associated with that particular particle itself. It is nothing that is imposed on it. So based on other, like you measure mass by weighing it. So there is a physical system which tells you that the particle has mass. Similarly, some of the particles do have charges. So charge is another physical entity basically. Okay. So if you talk about the case of an electron, electron has a charge of minus 1.6 into 10 raised to the power minus 19. Charge is measured in coulombs. Whereas, if you talk about the case of a proton, for the case of a proton, we have mass of a proton given by 1.67, not 3, let's say 1.67 into 10 raised to the power minus 27 kilograms, and the charge of a proton is exactly the same, that is 1.6 into 10 raised to the power minus 19 coulombs. When I am saying exactly the same, I mean the modulus or the magnitude of the charge is exactly the same. Charge carried by an electron is negative, charge carried by a proton is positive, right? So what is the basic difference? If we do not consider the sign of the charge, what is going to be the basic difference? If you see, the proton is around 10 raised to the power 4 times heavier than that of an electron, right? So if given a chance, if given a particular amount of force, the electron is going to be preferred thing which is going to be accelerating, right? Because electron is lighter, so for a given amount of force, electron is going to be the one which is going to be accelerating more as compared to the case of a proton, right? Further, we have defined about the masses, but let's assume that the force is good enough, so it should be ready to accelerate both the proton as well as the electron. Then why do we consider only in terms of electrons? Let me give you an example. If you again go back to this particular figure, here I have the nucleus, here I have the electrons. Now, the nucleus contains the protons. So that means the protons would be very, very strongly attracted, and that's the reason they are placed in a very small region of space, that's the nucleus. So since they are very, very strongly attracted as compared to the electron is lying outside the nucleus, so the force of attraction, or the force which is keeping the electron in its orbit, is going to be less than the force which is keeping the protons intact. Therefore, it is going to be much easier to remove the electron from an atom as compared to removing the proton, right? So I hope I have been able to convince enough that we have to discuss all the charge transitions only in terms of electrons, right? So if I say all the charge transitions are going to be discussed in terms of electrons, so what does that mean? It means that we will be left with two types of charges. One is a positive charge, other is a negative charge, right? So one is a positive charge, the other one is a negative charge. So what is the difference? How do we come to this? What exactly it is? So the positive charge is going to be produced from an atom. So basically, if you remove electrons from an atom, it is going to become positively charged. So loss of electrons results into a positive charge, whereas a negative charge is going to be produced by a gain of electron. So if an atom gains electrons, in that case it is going to become negatively charged, and if the atom gains positive charge, it is said to be, if it loses electrons, I mean to say, in that case we say it's going to be positively charged, right? So that brings us to the notion, to the conclusion of the notion as to what exactly are the charges. Taking this view further, obviously we need to understand how exactly are the charges going to be transferred and what are the physical properties. So let's first discuss about the physical properties of charges. So let's understand about the physical properties. So when we talk about the physical properties, the first thing, the charges are quantized. Let me explain what does that mean. So when we say that the charges are quantized, quantization basically means that supposing any particular atom has some charge Q, okay, and the charge of an electron is E. So the atom should be having a charge which should be an integral multiple of the charge of an electron. You cannot break up the charges further. You cannot say that the charge of an electron is less, the charge of any atom is going to be less than the charge of an electron, right? So Q is defined as equals to N times E, where N is nothing but an integer. It can be a positive or a negative integer, doesn't matter, but it has to be an integer, right? The first thing is that the charge is quantized. Then Then the next point is that every charge is going to be associated with some mass. So we say that charge is associated with mass. So every bit of charge that you see is going to be associated with some amount of mass, right? Because there cannot be any charge without a mass. Now, sorry, this was the point B. Now going further to the next point, that this is the point C now. Charge is a scalar. So charge is actually a scalar quantity. Okay? So it's not that it's a vector, you can just add or you can just sum of charges like normal things. So if it's a positive charge, you take it as positive, if it's a negative charge, you take it as negative. Okay? So charge is basically a scalar quantity. Then motion of a charge produces energy. Okay? So when we say that the motion of a charge produces energy, what does that mean? When the charge is moving from one point to the other, obviously there is a motion taking place and the charge is going to be radiating out. So it's going to be radiating out energy when it's moving from one point to the other, effectively producing an electric current. When there is an electric current that is flowing in a particular circuit, obviously there is going to be an electrical energy associated with it, right? So broadly speaking, these are the properties of the charges. We have already understood that there are, broadly speaking, two types of charges. One is positive, other is negative, right? Now, when we talk about, since we have now come to the conclusion that what are the broad important topics or broad important properties of charges, so let's take it further and see how can we detect charges. So, detection of charges. How exactly are we going to detect charges, whether there are charges or not? So a very simple experiment was done, which is famous by the name of gold leaf experiment. So I'll try to draw. Okay. So what we have is the following. Just give me a minute. So what we have here is the following. We have a metal top. Attached to this metal top is a very thin, wafer thin gold leaf, and at the ends are two very thin gold leaves attached to the same very point. Okay. Now what you do, okay, also another thing, this beaker that you see has a vacuum in it. So it is completely vacuumized. Now what you do is that when you bring a charged body close to this, so what it does as a result, so this charged body, when you bring it, obviously it induces charges. It does not need to be touching it. That just by induction, it's going to be giving the charge to it. So when the charge is going to be given to it, so what is going to happen? You will see that initially both of these gold leaves should be together, but as soon as you give the charge, you will find that the gold leaves have separated. They are no more at the same, they are no more together. So they have separated out. So when they separate out, we say that there should be some amount of charge that has passed through, and further we can diagnose that if there are similar charges, they are going to repel each other, because initially there was no charge. As soon as the positive charge comes in, the two plates just move apart, meaning thereby that there is a kind of repulsion that takes place when you have similar types of charges. Yeah. So this tells us about the detection of the charges. This was the first way when it was actually detected. Clear? Okay. Now moving forward, when there is a charge, we said that there is a repulsion that is produced as a result. So how do we quantize it? How do we put that into a mathematical perspective? So that mathematical perspective is defined as the force. The force that exists between two charges. Whether it's an attractive force or it's a repulsive force, we'll try to see now. So when we talk about the force, so for the force to exist, as we saw, we had the two gold leaves separating out. So if we take into consideration here, so if I say Q1 is one of the charges, I'm taking two arbitrary charges. So Q1 and Q2 are the two charges that are there. At any particular instant, let's say, they're separated by a distance r. Okay? So when these two charges are separated by a distance r, in that case, there should be a force that should exist between these two charges. So what are the forces? So if I say F is the force that exists between these two charges. So F should be proportional to the magnitude of charge Q1. I'm not saying whether it's a positive charge, it's a negative charge, or what type of charges. I'm simply saying that there should be a force that will be existing between these two charges. So the force should be proportional to the magnitude of charge Q1. It should be proportional to the magnitude of the charge Q2, as well as it should be proportional to some power of the distance. Okay? So F should be proportional to Q1, it should be proportional to the magnitude of charge Q2, and it should be proportional to inverse power of the distance. Why have I written an inverse power? Let me explain. If I bring the charges close together, obviously the force either of attraction or repulsion, just by common sense, tells me that it should increase. Whereas if I take the charges away, in that case the force should decrease. Right? So that tells me what? So we have the force that existing between these two charges should be inversely proportional to some power of the distance. I do not know as it because I am just proposing this rule. Okay? So taking this further, what we can say, So taking this further, if I combine all of this, so I can simply say F should be proportional to Q1, Q2 divided by r raised to the power n. Yeah? So when I am saying that force is proportional to Q1, Q2 divided by r raised to the power n, and if I remove the proportionality constant and say, let's say K is the proportionality constant, so K, Q1, Q2 divided by r raised to the power n, so this is the value of the force that we have. Right? Now, if I say that this is the value of the force, you can see that force has been inversely proportional to n. Now let's try to put it into a physical system. Let's take any two system, any two charges, and try to find out how much is the force that acts between those two charges. Right? So if we try doing it experimentally, the maximum value of force which matches the actual value comes out for n equals to 2. Okay? So if we put n equals to 2, we'll get the force as given by K, Q1, Q2 divided by r raised to the power 2. Right? So this is what is also known as the Coulomb's law. Okay? Fine. Now we'll take it further. So we have understood what exactly is the expression of the force. Now we have to further put some value to the constant K. So we just found that F is equals to K, Q1, Q2 divided by R square. So this is going to be true for all charges, but let's now try to think about it further. This force is a physical entity, right? Charges Q1, Q2 and R, these are all physical quantities. Now, if you remember, we had discussed about something like SI, system of units, CGS system of units. So in those system of units, so if I talk about SI system, force is going to be measured in newtons, charges are going to be measured in coulombs, distance is going to be measured in meters, right? Whereas if I talk about a CGS system, so in the case of a CGS system, what will we have? Force will be measured in dynes, charge will still be measured in coulombs, and the distance is going to be measured in centimeters, right? Okay. Now, how do you take care of this? The nature doesn't tell you that which system of unit you have to measure. The force between two charges is always going to remain the same. It is up to you as to which system of units that you would like to use, right? Therefore, putting across all these things into account, so depending upon whether you measure it in newtons or you measure it in dynes, what you find that the value of K comes out to be equals to 1 over 4 pi times another constant that is known as epsilon naught. I'll just explain that. So this 4 pi factor comes because of the SI system of units. So when you are measuring the force in newtons, in that case this 4 pi factor is going to be playing a role. So what will I get as a result? I'll get 1 over 4 pi epsilon naught Q1 Q2 upon R square. But what exactly is this epsilon naught? Let me give you an example. Let's say you have two balls, you're playing with them. You try to throw one ball towards the other, or let's say you're playing with one of your friends. He throws the ball towards you, or you throw the ball towards him with some amount of force, right? The two balls meet each other, so there is a contact force that is produced, right? So you can find out how much is there compression in the balls and so on. So how much will have in the contact force that will have been produced. Now, try doing it underwater or when you have a dense air. If you try doing the same thing, that is you throwing with the same amount of force and he throwing back at you another ball with the same amount of force, what you will find? You will find that the contact force between the two balls is going to be less. Why? Because the contact force is going to depend upon the density of the medium where the two balls are coming together, right? Same thing happens here. So if you have the two charges kept in vacuum or in air, in that case the maximum amount of interaction between the two charges can actually happen. The lines of forces from one charge can actually combine with the lines of forces from the other charge. So there is going to be actual combination, maximum amount of combination. But if you keep these two charges underwater or in any other medium, such that the force of interaction between those two charges decreases. So how does that decrease? That decreases because of the density of the medium, right? So to take care of that density, we put in this factor of epsilon naught. You will study later on in the electromagnetics theory that how this epsilon naught, and similarly for magnetic field we have mu naught, that is related to the velocity of light. So we'll study that later on. So effectively that concept comes from there. So this epsilon naught is what is known as the permittivity of free space. So for the value of air, its value is the minimum possible, and therefore the force between two charges is maximum. But as you keep on increasing the density, you will have a factor of K. So K is going to be known as a dielectric constant. So that will be basically related to the electrical density of charges, which are going to be affecting the force between the two charges. Hopefully that makes sense. Yeah. So we'll take it further from there. Now what is the value of this? Let me also write down. 1 over 4 pi epsilon naught has a value of 9 into 10 raised to the power 9. Okay. So from here itself you can find out what will be the value of epsilon naught. So this is the expression of force that we have come up to. Now let's go further. and try to associate other properties. When we say that force is a vector quantity, so obviously this force is also going to be a vector quantity. Therefore, the direction, so if I have two charges, let's say this is charge Q1 here, I have charge Q2 here, in that case, there is going to be a force Fq1 Q2, that is when Q1 acts towards Q2, is going to be equals to minus of F Q2 Q1, right? Therefore, this force is because of Q2 acting on Q1. Therefore, the general expression of the force is going to be given by a relation 1 over 4 pi epsilon naught Q1 Q2 upon R square with the unit vector R cap. So this tells you about the direction of the force. So this is the complete expression of the force, right? Okay, so far so good. Now we have come to the expression of the force. Now what next? Okay, the next thing that we now need to understand is what is known as the superposition law of forces. Basically, that's the same that we did in the case of vectors as well. There's a superposition law of vectors. So if I have to discuss about the superposition law of forces, so in this, what we are going to do, how will you find it out? Let's assume that on a particular charge, there is a separate value of forces that are acting. So the total force acting on a particular charge Q is going to be given by the force from another charge Q1, force from another charge Q2, force from another charge Q3, and so on. So it's going to be a vector sum, right? So it's going to be a vector sum. So it's not going to be that easy to solve further. So this is what is known as a superposition law of forces. This may sound very easy to solve, but let me give you the reason why it's not that easy. Let's assume that I have the charges. So let's say this is charge Q. Across this I have charge Q1, this charge Q2, this is charge Q3. I have discrete amounts of charges, right, all around this. So what will I have? So the next thing is I need to join this. So let's say this is R1, this is R2, this is R3. Okay. So the net force is going to be dependent on the unit vectors. As you can see, the unit vectors are not along the coordinate axes. So adding them up is going to be a very big hassle for you, right? So what I'm going to do in the next topic, next lecture, is I will tell you about how to break it up into components and solve further on that. Hopefully you enjoyed at this point. Thank you.